Hello everyone and welcome to today's session with title Earthquake Engineering, Advanced Design, a Finite Element Solution for Seismic Structure Design and Analysis. My name is Evelina Balkanoglu. I am Solution Technical Specialist at Greatech and I am also a Structural Civil Engineer. I hold a PhD in Computational Mechanics and I have worked in the past as a structural civil engineer in a consultancy. Here is the agenda for today. We will discuss the following types of analysis. First of all, the modal analysis. Then we move to modal response spectrum analysis, or RSA. The equivalent lateral force method, ELF, of course the pushover analysis, PA, and finally we will discuss the linear direct integration time history analysis. All those analyses can be used to calculate and assess the seismic forces in the structure and also obtain the seismic response of the structure. Before starting discussing each type of analysis separately, it would be nice to look at this diagram and see all the different types of analysis we have and we probably use for seismic design. We categorize the analysis to linear and nonlinear, of course. So on the nonlinear part, we have 4 different types of analysis. And on the nonlinear part, we have only 2. The ones marked with the green tick is the ones provided in advanced design and is basically the ones we will discuss in this session as well. So on the linear analysis category, we have the equivalent lateral force method, the modal spectral analysis, and of course we have the linear direct integration time history analysis. The difference between the first two and the third one is that the first two provide the maximum response, so they give the maximum value of the displacement, whereas or the response of the structure, to be more general, whereas the linear direct integration time history analysis provides a time dependent function of the parameter examined each time. From the nonlinear part now, we will only discuss the pushover analysis, and this type of analysis basically gives again the maximum response. Let's start with modal analysis. It's a linear dynamic method. Although we use the term dynamic, the results we get, it's not time-dependent functions of the displacements. It's basically an agent value problem as we know them from buckling, for example. The whole point is to define the seismic mass. Is basically the amount of mass that is going to be excited, and there are different rules in the Eurocode to do so. You can either allow for only the self-weight of the structure to be excited, or as the Eurocode suggests, to allow for the full permanent load plus some amount of the variable load. There are different parameters to define how much of the variable load is going to be added, and each seismic code suggests different values. The modal analysis can give 2 types of the results, either agent vectors or ridge vectors. We are going to discuss the difference between those two in the next slide. And of course, there is the following rule in order to be sure that modal analysis has been performed correctly. So the number of modes that the solver will provide us needs to be sufficient enough to meet the 90 or 95% mass participation. This is the requirement from the code. This requirement is to ensure that the response of all modes of vibration contributing significantly to the global response has been taken into consideration. So basically, we need to check after running a model analysis if there is the 90% mass participation. Otherwise, we need to ask for more modes to be calculated. Some information about the reads and the agent vectors. An agent vector analysis determines the free and damped vibration mode shapes and frequencies of the system. These natural modes provide an excellent insight into the behavior of the structure. The agent modes are most suitable for determining the response from horizontal ground acceleration. Though a missing mass, the residual mass mode may need to be included to account for missing high frequency effects. Mass participation is a common measure to determine whether or not there are enough modes. It's basically the rule we explained in the previous slide. The reads vector analysis, on the other hand, seeks to find modes that are excited by particular load. Reads vectors can provide a better basis than agent vectors when used for response spectrum or time history analysis that are based on model superposition. So basically, in a few words, the agent modes are related to the natural frequencies and can provide an insight in resonant effects, whereas the reads vectors should be used when performing a response spectrum analysis or time history analysis because they can provide a better mass participation compared to the agent modes. The load-dependent reads vectors are more suitable for analysis involving vertical ground acceleration and localized machine vibration, which is obviously out of the scope of this presentation. Reads vectors are also efficient and widely used for dynamic analysis involving horizontal ground motion, since for the same number of modes, they provide a better participation factor, which enables the analysis to run faster with the same level of accuracy. Further, missing mass modes are automatically included. As a result, no need to check for mass participation. Reads vectors converge much faster and more uniformly than the agent vectors. Let's see now another important term that has been implemented so far in this presentation, natural frequencies. Each structure has as many natural frequencies and associated modes as the degrees of freedom of the structure. They are commonly assorted by the amount of energy that is activated by the oscillation. The first natural frequency is that the one with the lowest energy level and thus the most likely to be activated. And when a mechanic frequency coincides with the natural one of the structure, any of those, we have resonance, which means that the deformations of the structure can increase in a very high level and cause the collapse, as we see on the image on the right, on the left-hand side, the collapse of the Tahoma-Narrows Bridge due to the resonance caused by a wind load, in this case, not seismic load. So the whole idea behind the modal analysis, apart from the use in seismic design, is also to know the natural frequencies of the structure and check for any resonance effects caused by either the seismic load, which is a dynamic load, but also any other dynamic load, for example, the wind, any machine vibrations, anything that can act in a dynamic effect in the structure. How to perform model analysis in advanced design? It is very easy. You need to set up the model analysis as an extra type of analysis that you would like to be performed. When selecting the model analysis, as we will see later when we will do the demonstration in the software, on the properties tab, you have all the different parameters that the user can change. For example, we can see the option of getting either agent vectors or load-dependent reads vectors, the number of modes. This changes accordingly, depending on which type of analysis we use or what type of seismic masses we select. Some convergence parameters, for example, tolerance of the maximum number of iterations. There is also the option to allow for the calculation of damping. This parameter uses the material damping that the user can set up in the beginning when setting up creating their own materials. So in case a material has a damping parameter that is different from 5%, when allowing for auto calculation on this tab, this damping parameter is used instead of the 5%. And also, there is the option to allow for the dynamic masses eccentricity. Basically, the Eurocode suggests to allow for some dynamic masses eccentricity. Is an accidental eccentricity of 5% in each direction for safety. And on the last image, you can see the combination of the dead loads and the live loads. We explained earlier in the definition of masses. Here the user can define which loads will be taken into consideration when defining the masses. Is basically to explain that when a structure is when a seismic load is applied in a structure, the user can define if those dead loads are going to be to vibrate with the structure or not. Obviously, any dead or live load is possible to be in the structure when a seismic load is there, compared to other types of loads that probably should be just combined with a seismic load, and they are not loads that they are going to vibrate with the structure. Let's see now how to perform a model analysis in advanced design. Here you can see a steel frame with 2 stories. I'm going to set up a model analysis, run the analysis, and we will see how to access the results in post-processor. The dead and the live loads have already been applied to the structure, so I'm going to set up a model analysis. Here, by selecting the modes, we have the options we saw earlier to change any properties. So I'm going to select the load-dependent reads vectors in this case, and I am going to select as the definition of the seismic masses the dead loads, and I am going to apply a 20% of the live loads on this combination. And I would like to allow the solver to calculate as many modes as needed in order to get the participation ratio on 95%. There is the option to ask for a certain number of modes, but in this case you don't have to guess. Basically, you just allow the software to calculate as many as possible in order to get the 95 participation ratio, and this option is most of the time recommended. I'm not going to change the damping here because I'm not going to perform any seismic analysis right now. So I will leave everything as it is. And I'm not going to add any masses and centricity for now because I'm focusing only on the model analysis, and I would like to show you how to perform the model analysis as it is. So now that I have implemented any modifications on the parameters, I'm ready to run the analysis. I'm running a finite element calculation analysis. And since the calculation has finished, I can now access the modes. The modes are now as a parameter related, such as the displacement forces, stresses. So if I select the modes, I can see the different modes the solver calculated. In this case, in order to get the 95 participation, mass participation, the solver calculated 19 modes. As you can see, the period of each mode starts from high to low. And by selecting the first mode, you can see that this is the first mode. The first mode is an out-of-plane one. So this is the most possible way of this structure to be deformed when it's going to vibrate. Here we have the second one. In the second one, we have, it seems asymmetric, the deformation is quite asymmetric, so we have the second beam to move out of plane in one direction, and the first one, the beam of the first floor, to move on the other direction out of plane. And if we keep doing this, we will get other types of modes, such as this translational one, or for example, a mode that looks like this, where both the beams and the columns have deformed. Let's see, the 19th is the last mode the solver basically calculated. By selecting the report and selecting the model analysis results, you can get the characteristic values for all the calculated modes. As you can see here, so for each mode calculated, you can get the pulsation, the period, the frequency, and of course the energy. And if the damping is different for each of them, you have the option to see it here. You don't get information related to mass participation, because in order to get those informations, you need to apply a load first. So when we will perform the seismic analysis later on, in order to get the mass participation, the structure needs to be kind of pushed by a load in order to get those informations printed from the software. So we will see that when adding a seismic load later on, we will be able to print the same table, but with another column that gives the information related to the excited masses, as we call it in engineering, the masses that are activated by each mode when this mode is activated. Let's move now to model response spectrum analysis, or as it's called, RSA. I chose to continue with the model response spectrum analysis because in order to perform this analysis, it is mandatory to perform a model analysis first. So it makes sense to organize and categorize those two one after the other. A quick overview of this type of analysis. It's a linear method that calculates the seismic forces along its direction using the participation of eigenmodes of the structures, the ones we defined earlier using the modal analysis. The seismic forces along its direction are calculated by the following equations, the ones we see on the right-hand side. And let's see what those parameters stand for. Gamma I is the participation factor for the I mode. SD is the spectral design acceleration for the period of I mode. Z is the damping parameter. So basically, this spectral design acceleration corresponds to a particular period and Z damping factor that corresponds to the I mode. M X, My, and M theta is the mass of the structure related to the examined direction. Is basically the excited mass, the mass that is excited due to this mode, the mode that the I mode, the one we examine each time, and Phi is the eigenvector of the I mode, the normalized one. The seismic forces calculated for its eigenmode are applied to the structure separately, and the response of the structure is calculated by the well-known equation, the balance equation. The real displacement developed due to this I mode, due to these seismic loads that come from the I mode, are given by this equation. And after calculating the U, the real U, the U that correspond to I mode, the internal force of the structural elements can be easily obtained. And finally, the internal forces due to its mode must be combined accordingly in order the seismic response of the structure to be obtained. The Eurocode suggests either this SRSS or the CQC method. Any of those can be used, and it's up to the user to know the limitations of those two and select the one that produces the best results. The whole concept behind this is each mode participates in the total response of the structure. So basically, we need to combine the internal forces in the end in order to get the entire seismic response. A quick note here, it is important to combine in the end, which means that the SRSS or CQC method needs to be applied in the final product, in the internal forces, let's say, for example, not in the intermediate products, for example, any parameters that are calculated during the process. Otherwise, the results will not be accurate. Let's see now how to perform the modal response spectrum analysis in advanced design. First of all, the seismic load family should be defined. As we see here, the seismic load family has 3 different directions, X, Y, and Z. And by selecting the seismic load family, on the right-hand side, we have the properties, and the user can select the spectrum, either elastic, unelastic, or even a user-defined. They can change different parameters related to the acceleration, ground acceleration, and the type of soil. So basically, this changes the spectrum, the representation of the spectrum. Also, they can change parameters related to the structure. such as the importance coefficient, the damping, and ductility class. And of course, here they can define the method of superposition, either the CQC or the SRSS method. Let's go back to advanced design now to see how to perform the response spectrum model analysis in advanced design. First of all, I need to create the seismic load family. Normally, if I haven't created the model analysis, when you create the seismic load family, the model analysis will be created automatically because it is mandatory to be performed in order to perform the seismic analysis. I'm not going to change any parameters in the model analysis. I will go to the seismic load family to modify any parameters that I probably need. I will leave the spectrum calculation as calculation 1. I'm not going to select the elastic spectrum. I prefer the unelastic one for now. I'm not going to correct the damping, and I will allow for 5% as the Eurocode suggests. I'm not going to change any parameters related to the structure here. And I will select the CQC method of superposition since it is sometimes more accurate compared to the SRSS. And I'm going now to run the analysis. Just a quick comment here, the seismic load family is the same as any other load family. It can be combined with the simplified combinations, for example, generator, and the seismic load family can be used in order to perform a steel or concrete design. So now I'm going to perform a finite element calculation to show you how to access the seismic results. The analysis has been performed, and here I can access the information for the seismic load case for the X direction, for example. I can see the response of the structure. It reminds me of one of the modes we checked earlier, and this is on the Y direction, and this is on the Z direction, the vertical component of the of the ground motion, the vertical component of the earthquake. We can also check the forces, for example, for the X direction earthquake, and it would be nice to see the bending moments, for example, in this particular frame. And as we discussed earlier, now that I'm going to print the characteristics of the model analysis, the characteristics value of the modes, if I generate the report now, we will be able to see the excited masses. So here on this table, we can see for each mode the same information: pulsation, period, frequency, energy, and now we see the amount of the masses that are excited in each direction for each mode. Let's proceed now to the equivalent lateral force method, or as it's called, ELF. A quick overview of this method is a simplified technique to substitute the effect of the dynamic loading of an expected earthquake by a static force distributed laterally on a structure for design purposes. It is quite similar to the one already discussed. Basically, instead of having all the eigenmodes and combine them, the superposition of the eigenmodes, we select the fundamental period τ1, the period that corresponds to the fundamental eigenmode of the structure. And for this given fundamental period, we calculate the base shear FB along the examined seismic direction, let's say, for example, the X direction. So the base shear can be calculated by this equation, where m is the total mass of the structure, sd is the spectral acceleration, either calculated by the elastic or the inelastic spectrum, and lambda is a parameter that follows this rule, which is either 0.85 or 1. In this case, the seismic forces are given by this equation, and they are a percentage base, basically, of the base here, B. And the relationship above is applied only for the components of the fundamental eigenmode that are parallel to the direction of the examined seismic motion. A linear distribution of base shear FB can also be applied instead. That is calculated based on this rule, where the J is the height of the J floor from the foundation level, and H is total height of the building. So instead of calculating the lateral force by this parameter, we can calculate the lateral force that is applied on each floor based on this factor multiplied by the base shear. Let's see now how to implement the ELF in advanced design. The ELF method is compulsory to be used in Canada and US. Is mandatory by the American Canadian seismic codes. So the advanced design has those possibilities. The particular functionalities that I'm going to show you only if you change the configuration to either US or Canada. So the calibrations I am going to show you for implementing the ELF method work only for those two configurations. So again, the same frame we saw earlier. I changed the configuration to Canada this time. I still have enabled the seismic load family and of course the modal analysis. And if I select now the seismic family, as you can see here, we can see a new set of parameters. For example, we can select the region, for example, where we are in Canada. I'm going to select anything just to make this work. This changes, of course, all those parameters. So I need to establish correctly here the total height of the building and the number of levels in order the software to calculate correctly the amount of the lateral force that is going to be applied on each floor based on the equation we saw earlier, this one. So the total height of the building is 6 meters since its floor is 3 meters and the total number of levels is 2. I'm not going to change anything else. I will allow For its seismic direction, the calibration, as you can see here, it is already enabled, is enabled by default. So this calibration here scales the results based on the minimum number of shear forces. And now I'm going to run the seismic analysis again. The calculation has been performed now. I can access the results. By selecting here, I can see all the different modes. The solver calculated for 95% participation, and for each direction of the seismic load, I can see either the mode that is the result that come from this mode when applied on this direction, or the quadratic superposition, and I can do the same for displacement, forces, and stresses. So two different ways of accessing the results here. Additionally, let's see now the x direction of the seismic load for quadratic combination, and for each mode, for example, separately. The first mode, if we remember from the model analysis, is the out-of-plane one. So I guess that the first one does not give any results, does not participate pretty much on the total response of the structure. Generating a report and selecting on the loading data the seismic analysis settings, we can see the calculated base shear based on the fundamental mode activated on its direction. So if I scroll down, and here in x direction, we see that the predominant mode is the second one. We can see the total excited mass is basically all the parameters needed in order to use the equation we saw earlier on the slides. We get the fundamental period, and the base here is calculated here. Let's move now to pushover analysis. The pushover analysis is a static analysis that uses a simplified nonlinear technique to estimate the seismic structural deformations of the structure. A pushover analysis simulates an earthquake by applying horizontal loads to the structure and is used to investigate how far into the inelastic range a building can go before it is on the verge of a total or partial collapse. A model for the building is assembled with all its structural elements, and material nonlinearity is also considered. Then a small set of horizontal forces is applied so as to simulate the effects of ground motions, and deformations are calculated. The forces are then increased in steps so as to develop a plot of base motion versus deformation. The pushover analysis is commonly used to evaluate the seismic capacity of existing structures, or it is also used for the performance-based design of new buildings in order to rely on ductility when designing for seismic forces. The pushover analysis sets the discussion for two different types of design: the performance-based design and the strength-based design, as we call them. Let's start with the strength-based design. On the left-hand side, you can see this graph where three different types of behavior are described. The elastic behavior. This is the behavior of a structure when we design using and assuming elastic behavior. Here is the real behavior. the real behavior is different from the elastic behavior because the structure will never deform, will never perform elastically. And the reason for this is the material nonlinearity. The material will yield as the structure will develop its internal forces. Therefore, we will never get this point. The maximum force the structure will be able to develop is the Fy, which corresponds to a force that is smaller compared to the Fe, which is the elastic force we would get if the structure would behave elastically. And of course, we have this curve, which is different from the real curve, and is basically the one we take into consideration when designing. The forces are smaller, of course, and because we don't have information about the stiffness of the structure, for example, in concrete, when there is cracks, the stiffness is reduced. The stiffness on the design is sometimes, as we see here, it is not assumed sometimes correctly. So we may end up with an overestimation of the stiffness. And here is the strength-based design, where we design for a certain force and we would like the structure to be able to stand for this, withstand this force. And on the right hand side, we have the performance-based design. The performance-based design is based on the fact we would like the structure to be able to demonstrate a certain amount of deformation. For example, on the top of this graph, we have 4 different icons that correspond to different types of deformation. On the first icon, we see a structure that has some damages. We can characterize them as minor damages, and in this category, we can assume that we have structures that they would like to be operational after the earthquake, for example, a hospital, and we would like those structures to be able to, of course, withstand the earthquake and have minor damages after the earthquake. So in this case, we would like those structures to be on this part of the curve, on the elastic limit, as we call it. So they need to be to behave elastically in an earthquake. We accept the damages, but we don't want the damages to be very serious. On the second and third point, which is a quite widespread part of the curve, we have the structures that we allow for those structures to have more serious damages. We don't mind to repair those damages. We don't mind if we need to not be able to habitate in this structure after the earthquake. So basically, we allow for a higher amount of deformations to happen after the earthquake. Obviously, we don't want any collapse. That's why we are here on that part of the curve. However, we don't want to be on the elastic limit. We don't want to have minor damages. We don't mind to repair. We don't mind to leave the premises if needed after the earthquake, if the structure is not operational anymore. But of course, we don't want to demolish the structure after the earthquake, or we don't want to have any collapse. And in this category, we have the houses, or for example, offices, anything that the people use in everyday life. It's not a building that we use for emergency, for example, as the hospital. So the buildings that we use in everyday life, most of the time fall into this category. On the fourth and fifth case, which are quite similar, we have the structures that they are not very important. For example, a very old structure. We don't mind after the earthquake to have extensive deformations, extensive damages. We are not planning to repair this structure. We are happy to demolish it after the earthquake if it is damaged extensively. However, we would like the structure to be able to develop its internal forces and resist the earthquake. At least give some time to the people that might be inside to leave the premises, so we don't have injured or dead people. So in this case, we allow the design to be on this part of the curve. And in the last case is the structures that we don't mind at all to collapse in case of an earthquake, so we design them at this part of the curve. How we implement the pushover analysis in advanced design? There are three different stages that the user needs to follow in order to perform the pushover analysis in advanced design. First of all, they need to perform a classic linear structural design because we need to determine the dimensions and the reinforcement of all the structural elements. And the reason behind this is since we are going to apply material nonlinearity in order to perform the pushover analysis, the sections and the dimensions of the members need to be defined in order to be able to apply the material nonlinearity afterwards. So first of all, we need to define this. And while we are defining the pushover analysis and the parameters that affect this type of analysis, two things the user needs to take into consideration. First of all is the lateral load pattern. Since we would like to simulate the earthquake loads, the loads are horizontal. We will see later the different options we have on the lateral load pattern. And secondly, we need to define the plastic hinges location and the characteristics of the plastic hinges. Incorporating plastic hinges, basically we incorporate the material nonlinearity. The second phase is to perform the calculation and then post-process the results. Lateral load pattern. What are the options? We have the uniform distribution, we have the linear distribution, and parabolic distribution. In advanced design, when selecting the pushover loads, as we will see later, we have all those four different options, and the fifth one, which is the user defined. In order to define these three options, the uniform, the triangular, and the parabolic, because they are affected by the height of the floor, we have on this structure the floors needs to be defined in order to be able to get those distributions. So basically, it is recommended to use the user-defined load pattern when no floors have been established. Normally, the Eurocode suggests to do two pushover analysis, one with a uniform load and one that is proportional to the first mode shape. However, in the demonstration later on, we will do one pushover analysis to show you how it is established in advanced design and run properly. Plastic hinges location and characteristics. The idea behind the plastic hinge is to add the material nonlinearity in the pushover analysis. So we assume that the plastic hinge is a spring, either rotational or normal spring, the axial spring basically. And we define the areas that we think that those plastic hinges will appear. Most of the time, the plastic hinges will appear on the ends of the structure elements. So we need to define at the ends of the beams and the columns the plastic hinges. In this case, are rotational springs, but in case, for example, of the bracing, they can be axial, non-linear springs. And on the right hand side, we can see the different graphs for those springs. So, for example, we see here a typical bilinear plastic hinge for beams that is used for beams and columns, and we have the different parameters explained here, and these parameters correspond to the previous graph we saw earlier about the damage limitation, the significant damage, and the damage that is near to collapse. So all those levels of deformation are connected, are combined with the different levels in terms of material nonlinearity back in the structural member diagrams, moment and rotation diagrams that we apply on the ends of the members. The American codes suggest a slightly different moment to rotation curves, but they still have the same concept behind, with the different levels we saw on the graph earlier about the deformation we allow on the buildings, depending on what we want to have after the earthquake. How we define the plastic hinges in advanced design? So basically, by selecting its member, we have the option plastic hinges, as we will see later on, and we enable the degrees of freedom that they want to have the plastic hinge. For example, here is a case of a beam or a column, and here is the case of a column actually, because we can see the letter C in the definition of the plastic hinge, and we can have the option to either auto-define the parameters of the graph or user-define them. As we can see on the right-hand side, we can see the same graph for this particular section, and we can see the different levels we saw earlier on the graph. Two important considerations about these plastic hinges definition. First of all, obviously, since they are plastic hinges, they can work for sections that they are class 1 or 2, and for sections that they are class 3 or 4, the user probably needs to take extra steps in order to be able to perform pushover analysis. Obviously, it's not the case, since the local backlink will be present when having a class 3 or 4 section. So basically, the whole point behind the pushover analysis is to be able to have sections that are able to perform plastic deformations and be able to develop plastic deformations, be able to participate in the plastic deformation of the structure. And the second tip here is to make sure you define the plastic hinges at the end of the elements and add the plastic hinge both at the end of the column and the beam, since we don't know which one will happen first. It's ideal to happen on the beams first, but since we are performing the pushover analysis, sometimes we need to define both ends in both cases to be sure that we have taken into consideration the material linearity in all the structural elements in order to perform the pushover analysis. Let's go back to advanced design now to see how to perform a pushover analysis in a structure. I have already created a structure here. I have a frame and I'm going to add the pushover loads in order to perform a pushover analysis. So first of all, the pushover loads can be added as a load family. From the tab that you can add any other load. And if I select the pushover loads, you can see here that we have the two different load types as the Eurocode and other seismic codes suggest. In my case, I have disabled the second one because for the sake of demonstration, I'm going to perform only one pushover. And since I don't want to define any floors at this point, I'm going to use this user-defined distribution. Additionally, I can select the load direction. So in this case, I have selected the plus X, but of course, the user has the option to select all the other directions as well and have pushover loads on different directions and perform actually a pushover analysis for different seismic directions. By selecting the pushover loads with right click, you have the option to automatically generate the directions and the loads. This is used when the load is a parabolic distribution, triangular, or a uniform, since the software uses the height of the floors to generate those loads. In any other case, the remaining one, the user-defined case of loads, the user needs to define the loads as you define any other load as point loads in the structure. So I have defined my point loads here, that they are applied on the top of its floor. And by selecting the pushover load case now, the one that corresponds to the X plus, I can access all those different information here. So I have the option to add eccentricity if I would like to allow for the load to be slightly eccentric. And here, since I asked for a user-defined load pattern, I don't have the option to change those information, but when the load is triangular, parabolic, or uniform, the amount of load is taken as a percentage of, for example, total gravity loads or any other load the structure has, or as a value force that the user can manually implement. The analysis stops when either a target displacement is met in a node that the user selects, or there is the collapse of the structure before this displacement has been met. In our case, I have selected as a node this one. Here is node 80. And I am going now to perform the analysis. I am going to change the properties of the pushover analysis as a nonlinear analysis. So here, by selecting the pushover analysis now, to modify the options. You have the option to allow for geometric nonlinearity if needed. Otherwise, you can change the analysis option. For example, change the maximum number of steps, the internal iterations in order to get accurate results, the stabilization iterations, and anything that can help the solver to work towards the accurate results. Before we perform the analysis, we need to add the material linearity, and that was basically what I forgot to add when going through this workflow we saw earlier. So I will show you how to do it in one element. And basically this needs to be done for all the elements in a structure. It's a very tedious process, but it is mandatory in order to take into consideration the material nonlinearity. So by selecting this column here, this one, I select plastic hinges, and I need to establish plastic hinges in both extremities. So here you can see this number, which explains it corresponds to the fact that we don't know exactly the location of the plastic hinge. So we know it's going to open on the ends of the column, for example, but we don't know the exact location. So this eccentricity is used to quantify this uncertainty. The definition of the plastic hinge. So basically, we see the graph we saw earlier, the moment rotation graph, and all those information have been calculated by the software for this particular section. This section is class 1. It's a section that has the option to deform plastically, and is a section that can be used to perform a pushover analysis. We are ready now to perform the pushover analysis. When selecting the pushover analysis, the still calculation is going to be performed automatically in order to get all those information about the sections and perform the pushover calculation. The solver is currently working and assessing the loads in order to perform the pushover analysis and create the pushover curve. As we see on the screen, it took 10 seconds to finish the calculation, and now when it stops loading, we will be able to access the pushover curve and see the results. I have established a seismic analysis at the same time in order to be able to see the difference between those two types of analysis. We already explained them. However, it is nice to see them graphically and to see the different type of information we get from each of them. The one that is based on the strength design, and the other one that is based on the performance design, as we explained earlier. So now we can access the information of pushover analysis as a load case. It is nothing more than a load case. So we can see all the different steps the solver did for this structure. So for example, if I would like to see the displacements, I can see in step 1 the displacements, and then I can move, for example, step 20 and see how much the displacements are. And I can see also, for example, for the seismic analysis I used earlier, I can see you can see the difference. So, for example, for certain seismic load, I have the maximum displacement distraction to get the 13.3, whereas when performing a pushover analysis, I can take the entire curve, the behavior of the structure, and then I can assess where I am on the design. For example, assuming that my seismic design is correct, I can easily say that from the pushover analysis, I am around step 4. So basically, step 4 corresponds to the seismic design I performed, and I need to double check, depending on the how important my structure is, if it is on the category of the structures that they need to remain in the elastic part, or are on the part of are on the category of the structure that they can have some plastic deformations. I can assess the situation and either accept my design or modify my design accordingly. On the post-processing, we can see the pushover result curves. We see a very typical pushover curve, the non-linear one, and then moving the cursor to the right, we can see all the different points and then see the base here for each of them and the deformation for each of them. We see the deformation in the end is massive. It's something that basically is really high because it means collapse. Let's finish now with the last analysis we will discuss today, the time history analysis. A quick overview about this type of analysis. Time history analysis is a dynamic type of analysis that provides, if it is performed linearly or non-linearly, the evaluation of the structural response in a dynamic way under a certain load, which may vary according to the specified time function, as we will see later when defining the load. The dynamic equilibrium equations given by this equation are solved using either modal or direct integration methods. In our case, it's the direct integration method that we are examining. And we can also set up initial conditions that come from a previous state of the structure. So, time history analysis in advanced design. Advanced design has the option to set up a time history analysis and solve it with the direct integration. The only thing the user needs to do is to set up the dynamic temporal loads. And we have different solicitation types the user can define. The arbitrary is to examine and study problems of impact, for example. The harmonic, which is suitable for cases such as vibrations made by a machine. And of course, the accelerogram that is used for the ground motions. We are not going to discuss the first two, since this webinar is targeted to seismic motions. I'm just explaining the other options the user have using this type of analysis and what else they can do using this functionality. Again, we have some properties that the user can modify here. We will check them later on when doing the demonstration for this particular type of analysis. And of course, some parameters related to the Newmark method, the method that the solver uses in order to perform the analysis and get the result. For those coefficients, here are some information. So basically, those coefficients are related to the stabilization of the method and the convergence. And here are the values of those parameters as they are proposed by literature. And we will discuss the ground motion only as a solicitation. Here we can see a typical accelerogram. The software basically provides a wide range of accelegrams the user can use. Two tips here. The first one, some of them are called scaled and some of them are called non-scaled. The non-scaled ones are the ones that are described as a proportion of the gravity acceleration, g. So in this case, when using a non-scaled accelerogram, the scale factor needs to be the g 9.81. If using a scaled one, this has already been scaled, so the scale factor needs to be 1. And let's come back now to the software to see how to implement the time history analysis in advanced design. I have a structure here, a frame, and I'm going to perform a direct integration time history analysis on this frame. First of all, I set up the dynamic temporal loads. You can define those here as you define any other load family. And by selecting the load case, here we can see the properties window we saw earlier when theoretically going through this method. Here on the solicitation type, we have all the different types we already discussed. And here we have the accelerogram. And by selecting here, you can define the accelerogram you would like to use. Normally, the start and the end come automatically from the accelerogram the user assigned. The interval needs to be something really small, so something around 0.001 is something that I suggest as interval. And the results, the internal forces, when the results will be printed, they will be saved at maximum displacement. Maximum displacements. Let's see now displacements for the temporal load, the dynamic temporal load case we implemented. So I have selected this node here, and I select the result curves, and I have selected the vertical displacement of this node. So I would like the abscissas to be time, and I select the same displacement again. And as we can see here, the displacement now is a time-dependent one. It seems quite similar to the accelerogram we apply to the structure, and we get the results to look like this. Before closing this session, I would like to do a quick conclusion. First of all, I would like to remind you the different type of analysis the advanced design supports. We have two different types of analysis based on the maximum response that they are linear analysis. We have the linear integration time history analysis, the linear one that is a time dependent, that gives a time dependent response. And of course, we have the pushover one, the nonlinear analysis decision linear analysis and can give you, of course, maximum response, and can be useful to perform the so-called performance-based design. There are other types of analysis, as we can see on this graph. I would like to thank you very much for participating in this webinar. I would be really happy to see you again in any of the sessions we organize, and I'm happy to take any questions regarding this session. Thank you so much.